In 1926, Edwin Hubble, already a prominent figure in astronomical circles, published a seminal work under the title Extra-Galactic Nebulae. This paper, presented to the American Astronomical Society, served less as a revolutionary unveiling and more as a meticulous synthesis of observations and evolving understanding, solidifying the concept of galaxies as independent island universes far beyond the confines of our Milky Way. To appreciate the significance of this contribution, one must traverse through the intellectual landscape of the early 20th century, a time when the very scale and structure of the cosmos remained shrouded in uncertainty. Prior to Hubble's definitive pronouncements, the nature of spiral nebulae, those faint, swirling patches of light observed through telescopes, was a subject of intense debate. Prominent astronomers like Carlo Shapley championed the single galaxy model, arguing that these nebulae were relatively small objects located well within the boundaries of our own Milky Way. Shapley's model, based on his meticulous study of globular clusters, positioned the Sun far from the centre of a considerably large Milky Way galaxy. This perspective, in essence, saw the entire observable universe as contained within a single, enormous stellar system. Opposing this view were astronomers such as Heber Curtis, who advocated for the island universe theory. Curtis, drawing on observations of spiral nebulae exhibiting significant radial velocities, argued that these objects were independent galaxies comparable in size and composition to our own Milky Way, residing at vast distances. The intensity of nova observed in these nebulae, which appeared fainter than expected if they were within our galaxy, further supported this perspective. The so-called Great Debate between Shapley and Curtis in 1920, held at the National Academy of Sciences, epitomized this fundamental disagreement regarding the scale of the universe. This debate, while lacking a conclusive resolution at the time due to limitations in observational data, served as a catalyst for further research and observation. Hubble's 1926 paper did originate the paradigm shift, but refined and solidified a perspective already gaining momentum. His meticulous observations, primarily conducted using the 100-inch Hooker telescope at the Mount Wilson Observatory, provided compelling evidence for the extraordinary distances of these nebulae. Crucially, Hubble identified Cepheid variable stars within several spiral nebulae, including M31, the Andromeda Nebula, and M33, the Triangulum Nebula. Cepheid variables are a class of pulsating stars whose luminosity is directly related to their period of pulsation. This period luminosity relationship, calibrated by Henrietta Leavitt, allowed astronomers to determine the intrinsic brightness of these stars and, consequently, to calculate their distances based on their observed apparent brightness. Hubble's calculations, meticulously detailed in his 1926 publication and subsequent papers, revealed that these Cepheid variables, and therefore the nebulae in which they resided, were located far beyond the estimated boundaries of the Milky Way. The distances he derived, on the order of hundreds of thousands of parsecs, firmly established that these spiral nebulae were indeed independent galaxies, island universes existing outside our own. 1 parsec is approximately 3.26 light-years, a unit of distance commonly used in astronomy to measure the vast separations between celestial objects. Hubble's measurements, though later refined with improved calibrations of the Cepheid period luminosity relationship, irrevocably altered our understanding of the cosmos. The methodology employed by Hubble hinged on the precise measurement of Cepheid variable periods and apparent magnitudes. This involved painstaking observations over extended periods, carefully tracking the brightness variations of these stars. He then applied the period luminosity relationship, expressed mathematically as a logarithmic function relating the period to the absolute magnitude, to determine their distances. A correction for interstellar extinction, the dimming of light due to intervening dust and gas, was also crucial for obtaining accurate distance estimates. While these early corrections were rudimentary compared to modern techniques, they represented a significant step towards accounting for the complexities of interstellar space. The implications of Hubble's findings extended far beyond a mere refinement of astronomical distances. His work shattered the prevailing view of a universe confined to a single galaxy. This established the existence of a vast, multi-galactic universe populated by countless independent stellar systems. This paradigm shift laid the foundation for modern cosmology, transforming our understanding of the origin, evolution, and ultimate fate of the universe. His discovery opened up entirely new avenues of research, prompting astronomers to investigate the properties, distribution, and interactions of these newly recognized galaxies. The immediate impact of Hubble's work was palpable within the astronomical community. It spurred intense observational campaigns aimed at identifying and characterizing other distant galaxies. Astronomers began to systematically catalogue and classify galaxies based on their morphology, leading to Hubble's own development of the now famous galaxy classification scheme, further refining his contribution to the field. This scheme, initially presented in his 1936 book The Realm of the Nebulae, categorized galaxies into elliptical, spiral, and irregular types, providing a framework for understanding the diversity of galactic forms. Moreover, Hubble's distance measurements enabled him to investigate the relationship between a galaxy's distance and its recession velocity. By combining his distance estimates with velocity measurements obtained by Vestis Liffer, who had earlier measured the redshifts of spiral nebulae, Hubble formulated what is now known as Hubble's law. This law, expressed mathematically as velocity equals Hubble's constant times distance, states that the recession velocity of a galaxy is directly proportional to its distance from us. This relationship provided compelling evidence for an expanding universe, a groundbreaking discovery that revolutionized cosmology and led to the development of the Big Bang theory. Hubble's constant, representing the rate of expansion as a a fundamental parameter in cosmology, subject to ongoing refinement and subsequent research, significantly built upon Hubble's original findings. Walter Baade, using improved observational techniques at the Mount Wilson Observatory, discovered that there were actually two distinct copulations of Cepheid variable stars, each with a different period luminosity relationship. This discovery led to a revision of Hubble's original distance estimates, increasing the size and age of the universe. Alan Sandage further refined the measurement of Hubble's constant through meticulous observations of distant galaxies and the development of more sophisticated distance indicators. The discovery of quasars in the 1960s, extremely luminous objects located at vast distances, provided further evidence for the expanding universe and the evolution of galaxies over cosmic time. These objects, powered by supermassive black holes at the centers of galaxies, demonstrated the immense energy output achievable in the early universe. The cosmic microwave background radiation, discovered by Arno Penzias and Robert Wilson in 1964, provided further support for the Big Bang theory, representing the afterglow of the early universe. Hubble's work also faced its share of critiques and revisions. His initial distance estimates were later found to be underestimated due to uncertainties in the calibration of the Cepheid period luminosity relationship and the effects of interstellar extinction. The value of Hubble's constant has been a subject of ongoing debate, with different measurement techniques yielding slightly different results. These discrepancies have led to a deeper investigation of systematic errors and the development of more precise distance indicators. Despite these revisions and ongoing debates, Hubble's fundamental contribution to our understanding of the universe remains undeniable. His meticulous observations and insightful analysis established the existence of galaxies beyond our own and provided compelling evidence for an expanding universe. His work laid the foundation for modern cosmology and continues to inspire generations of astronomers and physicists. In a sense, Hubble's meticulous nature reflects the essence of scientific progress itself, a constant process of observation, analysis, revision, and refinement, driven by a relentless pursuit of knowledge and a willingness to challenge existing paradigms. The direct influence on Edwin Hubble came from several key figures. Vestis Liffer's earlier measurements of the redshifts of spiral nebulae provided crucial data that Hubble later used to formulate his law. Henrietta Leavitt's calibration of the Cepheid period luminosity relationship was essential for Hubble's distance measurements. George Ellery Hale, the founder of the Mount Wilson Observatory, provided Hubble with access to the powerful 100-inch Hooker telescope, enabling him to conduct his groundbreaking observations. Hubble's work directly influenced numerous subsequent researchers. Alan Sandage dedicated much of his career to refining the measurement of Hubble's constant. Walter Baades' discovery of two distinct populations of Cepheid variables led to a revision of Hubble's distance estimates. George Gamow, Ralph Alpha, and Robert Herman developed the Big Bang theory, building upon Hubble's discovery of the expanding universe. The list continues for modern researchers who use space-based telescopes to measure more precise Cepheid distances. In conclusion, Edwin Hubble's 1926 paper, while not a singular revolutionary event, constitutes a pivotal moment in the history of astronomy. It was a culmination of years of painstaking observation and analysis, synthesizing existing knowledge and providing compelling evidence for the existence of galaxies beyond our own. His work transformed our understanding of the scale and structure of the universe, laying a foundation for modern cosmology and inspiring generations of scientists to explore the vast expanse of space. His legacy endures, not only in the scientific discoveries that bear his name, but also in the spirit of relentless inquiry that continues to drive our quest to unravel the mysteries of the cosmos. Hubble, in essence, shifted our cosmic address, revealing that our Milky Way galaxy is not the entirety of existence, but merely one island in a vast archipelago of galaxies, a profound realization that forever altered our place in the universe.